Okay, welcome back. Yep, connectedness. That's the thing for these classes, for these lectures. So what we did last time, well, there was this picture of what a connected space is, but today we're mostly going to use just the definition. So X is connected if whenever you can write X as U union V with U the open sets and trivial intersection, then that will force U to be empty or V to be empty. And we defined such thing where U and V are not open to be a separation. So that's only possible for not connected spaces by definition. So maybe I can say the separation of X, this we defined before, is a pair of opens open sets, opens U, V with X given by the union, trivial intersection, and both of them non-trivial. Then we also discuss a couple of other theorems, mainly when a subspace is connected. And then we discuss how the union of a collection of connected sets of connected subspaces can be connected if they intersect non-trivially. So yeah, today we're going to use some of these, but I just want to start with this theorem, just starting on a very high note. So what we didn't do yet with connected spaces is what happens when you allow functions, continuous maps. So if X is connected and you have a continuous map, and f from X to Y is continuous, what do you like me to say? Then, right, then it will be like Y to be connected. That'll be the naive claim. But then your function can be constant. So having a continuous function from X to Y is maybe not that important because you can make Y grow bigger, but you can be sure that the image of F is connected. So how you should read this is if you have a surjective map from X to Y, then Y is connected. And if X is connected, of course. So how do we prove such thing? Well, in principle, we need to consider open subsets of Y, blah, blah, blah. But the thing is, going from this function and claiming something about this subset will be just the same as going from the function co-restricted to its image and just talking about the function. So the first step here is, since the co-restriction, let's call this F co-restricted to its image, which is a function going out of X to F of X, is continuous, and of course, surjective. Right? Instead of proving that, we can just assume you have a surjective function. It is enough to assume or to prove the theorem for surjective, and this is the important part, surjective continuous map. G from X, and let's call this guy Z, because I don't want to say it's Y. Do you see what I mean when I say it's enough to prove this theorem in this case? What I mean is, if you prove this theorem for a surjective map, then you can apply the theorem to this function, which is surjective. That's going to tell you f of x is connected. And pretty much always that you want to prove something about the image of a function, you can assume it's surjective, because claiming something about the image. Okay, so let's prove that theorem. So in other words, what we want to show is assume x connected, and show that Z needs to be connected. Of course, assuming there is a surjective continuous map. Okay. So what I'm going to do, instead of proving that, I'm going to prove the contrapositive. Kind of a contradiction, but not really. So let's prove the contrapositive. So that will mean assume C is not connected, show X is not connected. So let's start with a separation of Z. So assume that we can separate this guy. Right? So that means U and V are open sets in C with trivial intersection, but they are both non-empty. That's the definition of separation. So I need to cook up a separation for X, right? Because I'm trying to show it's not connected. I need to cook up a separation. How can we go from these two guys to a separation of X? Well, the picture is something like, here's your C, where you have two pieces, U and V. Here's your X that you don't know. Right. You just do pre-image. You'll have some piece here. So suppose this is your U. You'll have a pre-image U. Suppose you have V. You have V here. And now we need to prove these two guys give you a separation. So in principle, they could intersect, and so on. But we need to prove that's a separation. So let's consider those sets. Since our function G is continuous, and these two guys are open in C, G inverse of U and G inverse of preimages are open in X. So we have open sets. Now from this, if you take preimage, left-hand side is going to give you X. Right-hand side, you know preimage behaves well with unions. So also, first thing is that X is the preimage of the entire C. That's for any function, don't need G to be continuous. And now I know what C is, preimage of the union. Preimage of the union is union of preimages. So at least we know we're not missing anything here. That's the first thing we proved. We proved that's your entire space. There's nothing else here. That's your X. And now when you compute the intersection of these two preimages, so this will be like the first part of the computation. This will be the second one. If you compute the intersection of preimages is preimage of intersection. But these guys form a separation, so that intersection is empty. and that's just empty. So here we didn't really use the G's surjective. That will be perfectly valid for our F that we started with. Where am I going to use that G surjective? I'm missing only one thing here. If I'm trying to cook up a separation, I know X is the union of these two guys, which are open. They intersect trivially. The only thing that I'm missing is, right. Now, why is that true? Why are pre-images not empty? Because G is surjective. So since U is not empty and G is surjective, the pre-image is not empty. And same for V. V is not empty, same thing, same thing. Pre-image is not empty. And that means we have a separation. Thus this expression here, it's actually a separation of X. And that's the proof. That's the contrapositive. Any questions? It's a decent proof. Probably the main trick is realizing that you can assume the function is surjective. If you don't do that, then you will have some tricks that or some computations that are maybe not ideal that you need to do. But once you realize something like that, that proof is quite straightforward. Everything works as it's supposed to work.
It's easier to separate it instead of connected.
Well, the answer is yes, typically, but not always, because there are examples that are very complicated. So yeah, but yes, in principle. So one is given an example, the other one is given a proof. Some people is very good at examples, some people is very good at proofs. Okay, so I want to write a consequence of this. Corollary, that's how you write this, hopefully, yeah? So corollary 2. Okay, what's your favorite surjective map? Or maybe flavor of map? There are two valid answers. Any other answer will make me very sad. Oh, then there's 3. No, that's injective. I mean, unless it's the identity, then. Yeah, co-restriction is always surjective, but there are surjective functions that are very important, and they're coming 2 flavors. That's also a good example, but that's not what I'm asking you to guess with no sort of hint. There are two things that you can construct that are surjective. Yeah. So I will give it to you because it's impossible for you to guess. So if you have an equivalence relation, and now you know what I mean, on a connected space, space X, then the quotient space X modulo the relation is going to be connected. And probably the hint that I could give you should be something like, well, you're going to ask me about this during today's office hours. So how do we prove this? Pretty much by definition, we have a continuous surjection namely the quotient map from X to the quotient space. Right, that's the, yeah, that's the what I call the quotient map. Some people sometimes call this the projection to the quotient space. For me, it should be called the quotient map. So it's just, yeah. Okay. So this means, I don't know, all of a sudden we know a bunch of things that are connected because we know, well, if you've been doing your homework or probably seeing the lectures about connected spaces, we know how to identify several things as quotient spaces, like the torus, like the circle, some other things. Okay. So two very nice theorems. Now, third one. Now, to be completely honest, I always wonder if I should mention this or not. Any surjective map looks like this. So these are all the surjective maps that you can have. Because you can always define an equivalence relation by two things are related if they have the same image under F. So corollary 2 is just the theorem, if you like nonsense. But okay, theorem 3. There is another kind of projective map that I could surjective map that I could consider. Not just quotient maps. There's another family of very famous surjective maps. That's the other one. So theorem, let's take X and Y be topological spaces. And then the claim is the product X times Y is connected if X cross Y is connected, then you can project to X and to Y. So that will imply X and Y connected. Maybe I can say both connected. Write this properly. But of course, for this implication, I wouldn't write theorem. The theorem comes from the other direction. Okay, proof. Let me just say this direction is apply theorem 1. You can project from X cross Y to X, and also X cross Y to Y. This is what I call P, maybe X here, P, Y here. These are surjective maps. So we're safe there. So the interesting one is the other. So what's kind of the intuition here? The intuition will be something like, if you cannot separate the product, then you cannot separate the two pieces individually. What's the meaning of that?
Separation in X cross Y. I mean, I'm sorry, that you're assuming there's a separation?
Yeah.
Separation existing within either X or Y.
Right. So I have a proof here, but I think I have a... So let me, let's do this. Let's do nonsense. So I have a proof here that's following the proof from the textbook mostly. But I have the feeling that there should be an easier proof. But probably it's wrong, because otherwise the textbook will know that. but probably this is going to be instructive. So here we need to assume X and Y are connected. Oh, there you go. Oh, yeah, I see. No, I was wrong. So yeah, that's very good. That's very, very good. So let's assume X and Y are connected. We need to show X cross Y is connected. Yeah. So yeah, that's the same. So the contrapositive of this will be X cross Y not connected, then either X or Y is not connected. Also makes sense, but not so easy to prove. So yeah, assume both are connected. And let's write a very nice proof. X, Y, connected. And we want to show X cross Y is going to be connected. And the idea from the textbook, which I'm just going to copy, is kind of tricky, but not really. So suppose this is your X and this is your Y. So what the book does is it's going to fix some B here. So B is going to be fixed, and you consider this space. So this should be your X, this should be your Y. You consider B, it's fixed. So this line is X cross B. So the first claim is, since X is connected, maybe I can say fix some B. Fix your favorite point B in Y. And here we go. First claim. Since X is connected, oops, I forgot to move this. Yeah, thank you. Since X is connected, what about the line? What about that line?
You can't say. There's no U in B that equals X.
Yeah, that's true, but if this is X, what's this guy? That's right. This is X cross B and nothing else. X cross B as a subspace of X cross Y, just taking the singleton B. So I'm taking X at height B. Since X is connected, then also X cross B needs to be connected. And now the question is why?
Inside the space of B.
Well, it's closed usually.
Yeah, but when you collapse Y,
Uh-huh.
using the space B, it's just a set with a single element.
Right, there's no topology on B. That's absolutely right. There's no topology on that point. So that's absolutely the answer. Yeah, there is a topology, but it's not really a topology. So this set is things in X comma something. That's as a set. Of course, these two things are the same, but also topologically, there's no topology on the point B. So the answer is, or why is this true? Because X cross B is homeomorphic to X topologically. There's nothing going on there.
You mean like crossing with B doesn't alter
Right,
X at all?
right.
Why doesn't it alter it? They're both the same properties with X.
So the question is, why is that true? Maybe the proof for this will be, we can define a map from X to X cross B, which sends a point X to pair X comma B. And of course, that map is going to be injective, surjective, continuous, and everything else. Right. And usually this is kind of an inclusion of X into the product, but it's not canonical because you are choosing B. So it's kind of depends on B. So you have Y times way of copying X inside the product. Any of those will just give you X. Okay, so X connected, X cross B is just X. So X should be connected. So what am I doing here?
Are you going to do this for every single element in Y?
Yeah, but what I'm claiming since X is connected and this guy is connected because this guy is homomorphic to X. Yeah, you're saying things that I don't really see the connection. So
can you fix something in X? Do the same thing? Like A, that's the same thing.
yeah, that's also okay, but why is this true? Why is it true that if something is connected and something else is homeomorphic to that first something, why is the second something connected? Uh-huh. Uh-huh. So the question now is, did we prove a theorem? Did we prove a theorem?
What, like 3 classes ago or something?
Someday, if something is blah, and then something else is homeomorphic to the first guy, is also the second guy blah. Never proved such thing. But you know it. Why? Because it just makes sense.
But if they're homeomorphisms, then they're basically the same space.
Absolutely true.
They keep the same property.
Absolutely true. Never proved that. And you're claiming that for any property of any topological space. And that's exactly how you should think about homeomorphisms. You shouldn't even try to prove stuff, should be obvious. So kind of meta theorem in topology and everything else. Theorem. Meta theorem. If X and Y are homeomorphic, then X is blah, which should be topological. So any topological property, if and only if Y is blah topological. Same blah. And you know this, and this is a theorem. Never prove that. And this is the sort of thing that I really don't want to prove. Yeah.
Doesn't homeomorphic mean like continuous, injective, surjective, and the inverse is continuous? So like if we have theorem 1.
In particular, yeah.
Yeah, in particular, theorem 1 would tell us that.
Absolutely. And I could say, instead of saying, that's exactly, yeah, thank you for the question, because that was part of the point. That thing is surjective. So we don't even need to go here. And that's I don't know what you were thinking, but I think you weren't trying to use this theorem. You just like, well, they are the same. And that's absolutely how I want you to think about these things. They are the same. So don't even ask me why that's true, because they are the same thing. So meta theorem, you can always use this. In some ideal world, I would ask you to prove that, but that's not me. If you don't feel comfortable, prove it. But it's just, well, do this sort of thing.
B is arbitrary.
B is any fixed point, yeah. Okay, that was a lot of nonsense, but at some point we need to have this discussion. Going back to our theorem, we have two connected spaces, X and Y, and trying to prove that product is also connected. The idea is you have a bunch of copies of X here. If you consider the union of all these guys, where you let B be something arbitrary, then you will take the entire space, right? But the thing is, if you let your B run through X, run through Y, then you'll get the entire space when you take the union. But that's not good enough because those guys do not intersect. So I need to make them intersect. And what's kind of the trick here? Well, instead of taking these guys, I will fix that one. And now I will take vertical lines. I will take all of them. And I will also consider their union with this red thing, because I want them to intersect somewhere. So let's write our second part of the proof is going to be for each small x, consider the vertical line, which is also connected. No, that's going to be one of the sets that I'm going to consider. But then I'm going to let the blue line move along horizontally. So now for each x, and this I need to make an x arbitrary, each x in the set x, we consider also the subspace singleton x cross y, which is also connected. So inside of x cross y, which is connected, again, because it's just homeomorphic to y, because that guy is just the same thing as y. Right? And not only that, when you take these two lines, they intersect. So if you do x cross b, and you intersect that with this little x cross y, they intersect at the point that you have here, which is exactly right, x comma b singleton. So that's not empty. So you have two subsets of a space which are both connected and intersect non-trivially. So by what we call proposition 3, lecture 17, you have two subspaces which are connected and intersect non-trivially. We know that this guy, the union of these two guys, namely that thing, x cross b, union little x cross y, is connected. And since that looks like a t, the textbook will call this t, but it depends on little x because b is fixed. So this guy is connected. And this is for every little x in big X. Okay, and now the hint here or the trick is, well, let's make this, so this entire thing is my Tx. The red line union the blue line. We know that's connected, just prove that. If you let X move along, you'll get the entire space, right? All of those spaces are connected and they intersect at the red line. So they intersect non-trivially. So now it's clear that when you do the union over all x in X of Tx, you get the entire space x cross y. That we could prove formally. How do you prove that? Do you see how to prove that?
Expand out the union.
Right, you take x comma y, that it's going to be live on this line, Tx, and then you can just move y. So x comma y lives in Tx. Okay. So this is because little x comma little y lives in Tx, of course, because or lives on this guy. So absolutely lives in Tx. Don't really need the red part here. If you move things line along, blue lines along, you get interspace. And their intersection is non-trivial. And the intersection over all x of tx, they all will have the red line. And then you'll be moving the blue line. So this just gives you x cross b. No. Forget about the red line. Forget about it. You have only the blue lines. And now move them. So red is only there because we want the intersection here. We're only putting the red line because we want them to intersect there. And this is not empty. So we're done. Again, by the same proposition, which is proposition 3 from last time, the union x cross y is connected. Because it's a union of connected space that intersect non-trivially. Yep.
Can I explain again why the intersection of dx is x times b?
Okay. Yeah, maybe we can prove that. So why is this true? This inclusion is absolutely clear, right? Because this guy is a subset of each tx. So this is for free. Because this guy is inside each tx, so also inside the intersection. Now, for this direction, if you take an arbitrary point in the intersection, so x comma y, maybe I cannot use x. Let's use a comma b in the intersection of tx's. Again, I cannot use a comma b. B is something else. I can use u comma v. So the only thing that I need to prove is that v is v. Because then u is something in x, we're done. So need to show v needs to be v. Okay, how do we show this? If you live in all these tx's, uv live in tx, which is x cross b union little x cross y, but for all x. So you cannot live here for more than one x because they are disjoint after one of those. Then you need to live here. And that's exactly what we want. Right? Okay, so that's the proof. Any other questions? Mm-hmm.
Clarify. So wait, when you go, like you explain, when you go in the other direction, say, but in
You mean the forward direction?
no, sorry. No, at the very bottom board.
Uh-huh.
You say let u be in the intersection of dx.
Oh, yeah, here. So what I mean is if you live in all tx's, that means you live in this union for every x. But on this sort of thing, if you live here, that means u needs to be x. So you can only live in one of these, namely when x is u. That means you live here all the time. U and v, u and v.
Like x is moving, right? And b is fixed. So like bx plus b is in there.
Yeah, maybe it's easier for me to write this. So in this case, so if this happens, either u comma v lives here, or u comma v lives there. Second option is only possible when u is x. But you live here for every x. That means you need to live here. Because you change x, it's not possible. Clear? Yeah, if it's not clear, think about that for a second. It should be an easy proof. Okay, so you should have some questions. Not about the proof, but about the theorem. What do you notice about that theorem that's suspicious? When we talk about products, what's the delicate thing with products? Right, but that's only important when? Right, when you are taking the product of an infinite family. If you have a finite family, there is only one topology because box and product are the same. So I need to say a couple of things. The first one is just a consequence of that theorem. So the first one is I'm taking product of two spaces here. I could take any finite number of them. So corollary, this should be 4. If you take topological spaces x1 through xn, so topological spaces, finitely many, then x1 cross xn is connected. Of course, that's going to imply each xi is connected because you can project, but it's only true the other direction. Xi connected for every I. So the proof should kind of use that and some induction. But I will not write that. So proof is use the theorem 3, and some easy induction. So that's something I needed to say, but then at some point we need to address the elephant in the room. What about infinite families? What about infinite families? What about theorem 3 when you take the product of an infinite family of sets of topological spaces? So theorem 3 remains true for infinite families. Again, one direction is always kind of for free. Forward direction, you just project. For infinite families, with the product topology, not true with the box topology. So not true for the box topology. Instead of writing that, I'll just write R to the n is not connected in the box topology. So there's one problem with this. Remember, R to the n means you do the real numbers as many times as you, so you have a kind of a ghost index here. One for each integer. So I'm claiming this is not connected with the box topology, which means that theorem is not true for infinite families with the box topology, but we don't know if R is connected. So that's something we don't know yet. So we need to explain or to study what's going on here. So connectedness in the real line. How do you feel about the reals? Are they connected? Absolutely true. How do we prove that? Yeah.
Well, think about the real, could you, well, because you could have singletons like 1 and 2, right? And then where you could have like you have a way where you define the covering by like singletons, so then there's no overlap. Where you have, because for it to be connected, you have it for the union of two sets to encapsulate the entire set, they have to intersect, right? You couldn't have like negative infinity to 1 exclusive and then 1 exclusive to.
Right. No, it's not separation. No. So how do we prove? So this is absolutely clear. This guy should be connected. We all know the real line is connected. Why?
You can assume that there is a separation by using two open sets.
Let's write the proof. So suppose reals U union V open sets, trivial intersection, both of them non-empty. Let's try to cook up a contradiction. So this is your real line. This is the real line. There you go, real line. You have some pieces of U, some pieces of P. They do not overlap. Maybe this is a very short one. Maybe this is your V forever now. What's the problem with this picture? Well, whenever they overlap, you have an empty space. What's an overlap? Well, I don't know. That's the problem with this. It's a very nice picture. I don't know how to make this thing into a proof. Right. This is absolutely a problem. This guy here cannot be in the red part because red part is open. Cannot be in the blue part. Right. Needs to be. They both need to be open. So this guy should be problematic.
So this is like the example I was thinking of where it's like, if you have negative infinity to some number and then that number to infinity, right? You can keep getting closer, but if it's exclusive, because it's open, you can't get that number, right? And then
Right, but also we don't know that that's how U and V look like. We only know they are open. So it's true that U cannot be negative infinity to 1 or to whatever we have here, point P, and then V to be point positive infinity. That's true. That's not a separation. But now this is an arbitrary thing. We need to prove it's not possible. So we need to use some stuff, and some stuff is, suppose you don't have U. What's this guy? Of what? Pretty much impossible to say what it is. You have something here. Let's call it V. There's some element there. You have something here. Let's call this U. What's P?
You'd say it's in the closure of both.
That's true, but how do we define P? Should be 1 point. We're trying to see. Yeah, it's something between U and V. How do we write exactly what it is? Probably I should apologize to whoever is watching these recordings, but I don't want to tell you the answer. What's P?
well, it can't be the intersection.
It's not. The intersection is empty. Yeah. Oh, I like that. It's absolutely not 1 over n. But what are you trying to say with that? Because I don't know. 1 over n might be, I don't know, maybe series here. I don't know. Yeah, we need to get close to the border between whatever this is and whatever that is. So the idea is, of course, this P is going to be none better than this P and none better than that P. And I'm not claiming there's a sequence here because this guy might end here. So maybe let's not use that P prime, P double prime. So what's this P? You need to consider all possible things which are inside your U when you take the entire interval, because I want this guy, not that guy. Yeah, but I don't want any S. I want to take the maximum possible S. So I need to take the supremum of all possible values such that this entire interval is inside of U. Right, so we need some analysis here. And that's what we're going to do next time. Let me write the definitions. So definition, I'm just going to use this for the proof. It's something you should know from analysis. So a subset, or maybe let's say, let A be a subset of the real numbers. And let's take M to be a real. So we say that M is an upper bound. You know this. For A, if A is more than or equal to M for every A in A. Yep. There we go. That's the other thing I want to define. Second definition is, this is a definition, but it's an axiom. If A is not empty, and admits one of these bounds, then it admits a smallest one. So it's the smallest upper bound for A. And that's what we denote the supremum. Denoted sup of S, of A. That there is some M like this. It's not a thing that goes all forever and ever. So I only have 3 minutes, but I want to. So I'm taking the supremum of all values S such that the entire interval from U to S is inside of U. We're going to write that next time, of course. That we need to cook up a proof there. The supremum cannot live in U nor in V. That's what we're going to prove. It exists, but union V gives you everything, and you can say that supremum is not. It's not possible for it to live in U nor in V. But yeah, we will write the proof next time. So it's I'm not even saying why those things are true. But notice it's kind of frustrating how hard it is to prove the reals are connected. I don't know how you feel about that. Yeah.
We had a lemma last time that said if the only subsets of a set that are both open and closed are the whole thing in the empty set, then we have connectedness. And I'm wondering if we could try to show that for the real, the only open sets are the whole thing in the empty set. And even though thinking about open set in reals is like hard, thinking about basis elements or sub-basis elements for the reals, like pretty easy. So I'm wondering if we could go from like what we know about the basis or sub-basis elements.
Yeah, it's kind of easy to prove that it's not possible for a basic open for an open interval to be closed. That's very easy. That's not telling you about nothing about the union of all those guys. That's exactly the problem. But no, notice it's not that complicated. That's what U and V could look like.
That you think that the only open sets are empty and the whole set. So you could theoretically keep giving examples where they'll prove this because is not open, right? Then at that point, you're just proving that any arbitrary interval set open. I think that is like you're not just saying you prove that pretty much. Well, I think I could prove that any arbitrary interval or any is non-open, but going from there to any arbitrary set is not open.
Absolutely. Absolutely. Okay, so last 2 minutes. What I want to say is you've seen this sort of proof. So remember, if you ever so a proof for this theorem, the intermediate value theorem, this tells you something like let f from the reals to the reals be continuous. You don't need the entire reals here. It's enough to have an interval. Suppose you have A smaller than B. It's not important. I just want to have an interval. The claim here is if you have any value between, maybe let's assume f of A is smaller than or equal to f of B. Otherwise, I don't change things. Well, there is some generality because I'm also assuming A is smaller than B. So the claim is then for every value in well, smaller than f of A, bigger than f of B, maybe smaller than or equal to, there exists some C with between A and B such that f of C is R. So what we're saying here is you can catch all values. So I'm not saying exactly why, but if once we know the reals are connected, or probably that any open interval AB is connected, then this is going to be for free. But the proof of this theorem, if you go back to your analysis class and see the proof of this theorem, it's exactly what we're going to do here. You have this exact same sort of problems. Actually, proving this is more complicated than proving this, because you have functions doing stuff, and here you just have intervals. Right. What we're kind of proving is right, exactly. The image of this guy is going to be connected. So if you have two things like this, then you cannot have any gaps in between, and that means you're going to catch this guy with the image of f. We know image of connected is connected, so that there can be no gaps. Very different. Yeah. But let me hit the record, stop the recording, and then we can discuss.
That's the first one. Like